Hi everybody, welcome to lecture 2 on Multimediale Werkzeuge, this time on communications. So we have digital communication networks like the internet, so we communicate over the internet, and for that we have different protocols, and those protocols we will see today. For instance, for the World Wide Web, for the browser and such. So when you look at the history, it all started with the ARPANET and the TCP/IP protocol. So first was the ARPANET, and ARPANET is the Advanced Research Projects Agency Network, and this was the first packet switch network. There the data is divided into packets and is given a destination address in the header. And before that there was only circuit switching. That means we have a fixed connection, usually telephone lines or modems. The problem there is the communication is difficult between multiple computers, to and between multiple computers. So if you have just one connection, then you would have to basically end this connection and build a new connection each time you want to talk to a different computer. And if you have to do it often, then this becomes quite cumbersome. So the first ideas were formulated by G.R. Licklider of BBN in 1962 already, in a paper about the galactic network concept. Right, so that was kind of sci-fi at that time. So BBN is a company in Cambridge, Massachusetts, and it's for Bolt, Beranek and Newman, the founders, who made digital data transmissions and later also pioneers of speech coding. So they used digital data also then to transmit speech later. Yeah, so the first ARPANET, first was the ARPANET, and basically here are some milestones. So starting from 1969, they had connections between the University of California in Los Angeles, the Stanford Research Institute, the University of California in Santa Barbara, and the University of Utah. Right, so basically in 1969 that was all that was connected to the internet, although at that time it wasn't even called the internet. The name internet was not coined yet. It was called the ARPANET. So basically this connection started in 1969, and then the first email from Queen Elizabeth II was sent on March 26, 1976 already. So she was quite modern. It was also a popular application for the National Science Foundation. It was about networking of supercomputers and computers of the computer science faculties, called CSNet, and that was connected to the ARPANET. So it turned out that for the NSF, this networking was also very useful, because then they could easily communicate to those computers and to those research groups. And in about 1984, there was the emergence of the term internet. So that's when the name internet was born, basically. So that actually was a lot later than, say, the first email from Queen Elizabeth. Yeah, and characteristic of the internet is the so-called Internet Protocol Suite, which contains TCP/IP, among other things. And that developed from work done by DARPA in the early 70s. Right. So in 1973, Vinton Cerf, developer of ARPANET, Network Control Program, has developed an open protocol with CAN. And important features were the differences between different networks were hidden behind this protocol. and the result was the TCP/IP protocol. This made it possible to connect the most diverse networks, and it was used in 1975, first between Stanford University and University College London, so across the Atlantic. And in 1983 it was generally introduced in the ARPANET. So that made it now open for more networks to connect, because now they had a common language which all the networks could understand, and this language was TCP/IP, the TCP/IP protocol. Yeah, a further data network with significance for the internet was the AloaNet. So, sounds like Hawaii, and actually it is. Norman Abrahamson was a professor at Stanford University and a passionate surfer. He went to Hawaii to work on radio-based digital communications. Radio-based to ensure data communication between the islands. Right? So Hawaii is not just one big island, it consists of several islands, and they want to communicate, they want to connect their computers between those different islands. And because the distance between them is actually quite large, it's best to use radio to connect them. Yeah, so the communication between different data stations was originally circuit switched, like the telephone, with dedicated connections for each participant or each computer. And if you use radio, that means everyone has their own frequency, right? So it's basically really like radio. When you listen to the radio, every station has their own frequency. The problem is, the more participants, the more bandwidth is required, and the more expensive the transmitters and the receivers become. So if you have more stations, you need more frequencies. The problem is also the availability of frequencies. Usually you have only a certain band allocated, and that means that limits the number of possible stations that can transmit on those frequencies. This is called frequency range multiple access, or short FDMA, or frequency division multiple access. So this would be a division. Yeah, the other option for cheaper transmitters and receivers is that each station gets its own time slot. And this is called time division multiple access, or short TDMA. So that means every station uses the same frequency, but only a certain time slot. So station A transmits, say, at second 0, station B transmits at second 1, and so on. The problem here is the possible data rate decreases with the number of participants, even if they are not transmitting. So you would have to wait until all the stations had their time slot, and then you can transmit again. And if it's more stations, then you have to wait longer. So AloaNet took a different approach, similar to TDMA, but not with fixed time slots, but flexible. So in this way it became less dependent on the number of stations. So this is the first AloaNet protocol. So this is how it goes. If data exists, send data. If there was a collision with other data, repeat later at a random time interval, and hopefully then it works. So basically it's just a trial and error approach. A station that has data just sends, and if it didn't work, it just tries at a random interval later. Simple enough, but it actually worked. So it's a very simple protocol, but it actually works. And it was later in the Ethernet protocol supplemented by CSMA-CD, which means carrier sense multiple access collision detection. So basically then the transmitter first listens if the channel is free, which actually makes sense, right? And that actually helps a lot. Yeah, and this is also the basis for the Ethernet, or the local area network, local networking of computers, and also the wireless LAN, wireless local area network. Same protocol. And because there can be collisions, that means we also have a maximum throughput from statistical calculation, which is approximately only 18 to 35% of the maximum possible data rate. So this comes from all the collisions and the wait times for the free channel. So this fundamental problem still exists today, for instance, in wireless LAN. The achievable data rate at, for instance, 802.11b for several wireless LAN stations is about 2 to 4 megabits per second, even though the maximum possible would be 11 megabits per second. Right. So this is also true for the newer standards. They have now higher data rates, but still it's about the same fraction that you get for a usable transmission rate. Yeah, so that basically comes from this principle. Yeah, and then some key milestones. The work on AlloNet started in 1970, and in 1972 AlloNet was connected to ARPANET on the mainland. So basically connecting to California. And that means we had an early networking of networks. So that's also an early start of the internet. AlloNet also shows simple reasons for splitting the data into time-limited packages. This makes it possible for other stations to gain access to the transmission medium at the end of the packet. Otherwise, there might be a very long waiting time. Yeah, and these protocols are organized in the so-called OSI model. So far we had the TCP/IP protocols. This is short for Transfer Control Protocol or Internet Protocol, and the Ethernet. Right? So how do they relate to each other? This is organized by the OSI, the Open Systems Interconnection Reference Model, and it partitions it into layers. Right? Here you can see the layers. So the highest layer, number 7, is the application layer. Examples are FTP, HTTP, POP3, Telnet. So here FTP is file transfer, HTTP is for web pages, POP3 is for email, and Telnet is for remote logging into computers. So these are applications which are using the internet. Then just one below, layer 6 is the presentation layer or syntax layer. Number 5 is the session layer. Number 4 is the transport layer. For instance, example, TCP or UDP. So here we have our TCP again in layer 4. An alternative is UDP. We'll come to it later. And then just below in layer 3 is the network layer. And this is where we have IP, the Internet Protocol. Currently we have IP version 4 and we also have IP version 6, and both coexist. Then below that, now we are coming closer to the physical layer. Layer 2 is the data link layer. This is the Ethernet protocol and wireless local area networks. So this is, for instance, where the protocol for the AlloNet would be. Then the lowest layer, number 1, is the physical layer. So this is the connections that you actually have, that your computers are now connecting with other computers. So there's still some German name left here, data connection. So these might be connections that you use, say, from the university to some data center. Yeah, and you can also read more about it in this Wikipedia link about the OSI model. Yeah, so the function of TCP in the transport layer, layer 4, is to split a data stream into packets with a predetermined maximum size, and to transfer the data to the IP function, the Internet Protocol. Right, then the IP basically you can think of as another function in your operating system. TCP is a function or a program in your operating system. It takes data from an application. TCP processes it and then gives it to the IP function of your operating system. Yeah, and this checks whether packets are lost and that the sequence is correct by assigning a sequence number. The TCP protocol, it checks whether data is okay by adding a checksum. TCP on receiver side gives acknowledgement if packet was received successfully, and TCP repeats packet if acknowledged was not received within the timeout time. So basically the TCP, the transfer control protocol, takes care of the transfer of bits from the application to the application on the other side. And below that it uses IP to do its task. Yeah, alternatives to TCP is, for instance, the mentioned UDP. This is short for User Datagram Protocol, for applications such as streaming audio and video. It allows the application to perform many of the functions of TCP. For instance, for audio and video, you don't need the acknowledgement because there the loss of some bits might not be so bad, but it would be bad to delay the transmission because it has to wait for an acknowledgement. So for streaming it would be more important to have just lower delay, and then if data is not arriving, just to discard it. So this is what the UDP allows the application to do. Another alternative is ATM, Asynchronous Transfer Mode. It's a timing-based protocol and it's suitable for fast transmission of real-time data, like telephone speech data. So this is important for low delay, and it's still used in basically in the physical, in the network physical layer. Yeah, then we have the transport layer, layer 4, and the network layer, layer 3. So yeah, the transport layer was TCP. Network layer is now IP. Right. So IP is short for Internet Protocol, and this basically takes care of the addressing of our data. So the function here is to address data stations or computers. So here's a link to NetPlanet, a German link, and now we have those two different versions of protocols. IP version 4, which uses 30-bit addresses, approximately 4 billion addresses can be addressed with 32-bit. And in IP version 6, also called the next generation internet, it has 128-bit addresses, so many more. So this is also why IP version 6 is now more and more used, because the 30-bit get to its limits. The extension of address fields to IP version 6 is necessary due to the exponential increase of data devices on the internet. So you could say, what happens to version 3 and to version 0 to 3? They are not used or reserved, and version 5 was experimental. Yeah, so that leaves us with IP version 4, addressing with 32 bits, and those 32 bits are 4 bytes. 1 byte is 8-bit, remember, so 4 times 8 is 32, and 1 byte is also called octet because it consists of 8 bits. Yeah, that gives us the maximum possible number of addresses, 2 to the power of 32, and it's this number here. So it should be actually without this. So this is the possible maximum number of addresses. And the representation usually is done as 4 bytes with dotted decimal notation. So remember, each byte, 8-bit, has numbers from 0 to 255. So each byte is then represented as a number from 0 to 255, and then they are separated by a dot. So it can be seen here. So here are the 32 bits as an example. And here's the dotted decimal notation. So here you can see the 80 is the first byte, those bits here. So we have those 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. And this corresponds to the decimal number 80. Next, here the blue one, again 8 bits. Here corresponds to the decimal number 245. Then here the next byte, 8 bits, decimal number 65, and here decimal number 1. And they are separated by the dot. So I guess you've all seen this type of notation. This is the typical internet address notation. Yeah, and also here you can see it has some structure to it. So the first at the beginning is the host ID. Then we have a network identification ID, and the last one is the computer. So the number of bits for the network identification is actually variable. So it's not fixed, as it might appear from this picture, but it's actually a variable. So you can read more about it in this link here. Right. And this is an example. For instance, the TU Ilmenau network starts with 141.24. So now we have 2 bytes to address the TU Ilmenau network. So it's, here you can see the red and the blue would correspond then to the host ID of the TU Ilmenau in our case. In comparison, the Massachusetts Institute of Technology, one of the pioneers of the internet, they just have the first byte as identifier for their network. So the number 18. So for the MIT, that means just this red part would be the host ID, which has the advantage then that there's more for the rest, right, for the computers inside the MIT. Yeah, so for the TU Ilmenau, we have 2 bytes to address all the computers inside the network, and for the Massachusetts Institute of Technology, we would have 3 bytes and correspondingly more addresses. Yeah, we can also find out our own IP address, for instance, with the link what's my IP. So I can actually try. Let's see if it works. I need to open a browser. So I'm opening Firefox here. Let's see if that works. And paste this address. And let's see what it shows. Yeah, so here you can see now my public IP version 4 address is this. So this is how you can check it. And you can see this is not the TU Ilmenau address because I'm not at the TU Ilmenau right now because of the corona restrictions. Okay. Yeah, so there you can also find further information and commands for different operating systems. And And we can display information about an IP address in Linux, Unix using whois IP address. So we can open a terminal. So now I just open a terminal and then I can try whois. And it gives me some information, how to use it. And what it wants to have is the address of a host. So I could say, for instance, whois www.tu-ilmenau.de. Oh, I forgot. Status invalid. Let's try the IP address that I just found for myself. This one here. Here we get some more information. So here you can see it's a telecom address. The address was assigned by our IPE and some more details. Yeah, so here you can get some information about the address range. Under Windows, it's only available as download and not as a part of the operating system. Right, so it also shows that Linux is more made for networking than Windows. We can also display the route of data packets with delay times using under Linux the command mtr, short for my traceroute. For instance, mtr, and then we try to find out how the connection to the Hochschule Sachsen-Anhalt is. Copy. And going back to our window, our terminal window, and paste it. So here you can now see how the connection is done. So it starts with my Fritzbox here at home, and then it goes into the internet here using Versatel. Here you have some anonymous addresses, and then it goes in the Deutsche Forschungsnetwork, so the university network here. And let's see, what else do we have? Don't know what this is. So this already is Hochschule Anhalt, Sachsen-Anhalt. And here we are basically. And we can see no packets are lost. And here are the ping times. This is the times in milliseconds that it takes to reach the host. So here we can see average, we get about 50 milliseconds. So 50 milliseconds is not too bad, but it's also not too great. 50 milliseconds is, for instance, quite okay for teleconferencing. If you want to play music over the internet, this would be already kind of too high. And also for gaming, this would be kind of too high already. Yeah, so with Q I'm getting out of it. This is also interesting. See what happens if I try an American address, www.mit.edu. Let's try. So let's see if we can get to America. So here I'm starting with my Fritzbox, going through some anonymous servers here, and then I'm getting an Akamai server here in Germany, DE. So that means the website of the MIT is mirrored to an Akamai server in Germany. So actually we are not even going across the Atlantic, we are staying in Germany for reaching this website. And this is actually common practice. If you have websites which have high traffic, then it makes sense to mirror those websites on several places in the world so that we have distribution of the traffic. So here in this case we have a server, Akamai server in Germany doing it. And we have actually less travel time, less delay time to this Akamai server, just 20 milliseconds on average. So that's not too bad. Okay. Yeah, so where do we get our IP addresses from? And the global and highest instance is the so-called Internet Assigned Numbers Authority, IANA. And it delegates IP addresses to regional internet registries, the RIRs. Right? And this is what we just saw with who is of my address. There you could see RIR. So this is for regional internet registries. Yeah, and there we have the American Registry for Internet Numbers, ARIN for North America. Then we have the RIPE for Europe, Middle East and Central Asia. Then we have the APNIC for Asia and the Pacific region. Then we have the LACNIC for Latin America and the Caribbean. And we have the AFRI-NIC for Africa. So basically each continent has its regional organization for assigning the numbers. And you can also read more details about it here in this link. Yeah, and this leads us to the domain name system, DNS. So far we had numbers. Our data device is identified by numbers, which is the IP address. So that's good for machines, but bad for people, because it's hard to remember. Plus, IP addresses can change daily, as with most DSL connections. So we just saw my DSL connection IP address with what is my IP. But this address is not valid tomorrow. Right? Tomorrow I will have a different address. So it's not good if, for instance, I want to host a website. Then every day my website would have a different address. So the solution here is the domain name system, the use of domain names, which is easier to remember than the numbers. Right? So for instance, www.tuilmenau.de. So this is the domain name system. It stores information associated with domain names, with who is. So this is what we just saw. And it translates domain names to IP addresses with the command or the function host. So if I type www.tu-ilmenau.de, then the function host knows which IP address belongs to it. So it's basically a translation. And earlier this translation was done locally on each computer, and for that each computer had the file hosts.txt or lowercase hosts under Linux Unix. So this is the name here. Yeah, so this is very convenient for the local computer, but the problem is what happens if there are changes? Then the files must be changed on all the computers. So if I have a new device or something else changes, I have a new website or whatever, then all the computers would need to make changes. Yeah, but this system is still used as a supplement in computer systems, in Linux or Unix under /etc, in Windows under /Windows/system32 and so on. So you can actually still see it, but usually it's not used. So that's because the local hosting of those tables is not practical. It was later done on servers at central locations in the internet, and that was invented already in 1983 by Paul Mocker-Petris. And you can see more about it in this Wikipedia link under domain name system. So here's an example. display the IP address of a domain name. In Linux, Unix, the command in the terminal is host, and in Windows the command is DNS lookup. So for instance, find the IP address of the following web address: www.tuilmenau.de or www.mit.edu. So let's try. So I'm now trying out the host function. Going back to my terminal here. Yeah, so here you can see it. Basically it returns this IP address. Input is this domain name, and output is the IP address. And here you can now actually see this 141.24 as the address for the network of the TU Ilmenau, right? So this is exactly the first 2 bytes which characterize the network of the TU Ilmenau. And then the other 2 bytes basically are for the web server of the TU Ilmenau. So now we try MIT, the website, where we just saw the Akamai server. So indeed, we get some Akamai addresses. So we actually get a few addresses here. So www.mit.edu is an alias for www.mit.edu.hkey.net, and this again is an alias for this Akamai network. So here it's already mapped to Akamai, and this has this IP4 address, right, 104.86.50.50, and it also has this IP version 6 address. So now you can see how an IP version 6 address looks like. Remember, instead of 32 bits, we now have 128 bits, and the notation is also slightly different. This is a hexadecimal notation, where each 4 byte are represented by the digits from 0 to 9 and the letters from A to F. Right? So E is corresponding to 4 bits. So EF, F would be 4 ones, so E is 3 ones and a 0. So you can see how those IP version 6 addresses look like. Yeah, so they must be longer, and they also decided to use a different notation here. And indeed it's Akamai. Yeah, so this picture shows how it basically works. Right, so here we have a device which looks for an address. For instance, where is www.wikipedia.org? And then it first tries the first root name server. And this says, this is at this address here. So this is usually associated, for instance, with your Fritzbox. The Fritzbox has a name server built in, and that gives you an answer. So here this is the answer, and then it goes to this device named here. That's, for instance, the org name server, and that gives another answer here. And then it tries this server here from wikipedia.org, and that gives us the final address. So it's a stepwise process. Yeah, so now we have our DNS system. Further applications for the internet basically is SSH, is for secure shell. This allows to open a remote shell to another computer. And this is basically what I just did here, right? I have a shell. This is my terminal shell, and using SSH, I can now log into a different machine, right? So you can read more here in this Wikipedia link. And for this, you need either the IP address of the remote machine or its DNS name. For instance, we can open a terminal window, as I just did, using alt minus control minus T under Debian Ubuntu Linux, and then just type, for instance, one of the machines of the TU Ilmenau. So we can try it here. Copy. Then open my terminal here. Paste. So now it asks for my password, and then I'm logged in basically. So I can try. Nope. Let me try with a different username. So here you actually can give it a username add, machine name, and then try the password. Yes, so now it worked. So now you can see I'm logged into this machine, and I can now work on this machine just as if I was sitting in front of it. So that's very practical. I can do basically everything I want on this machine. And another practical property is that I can also open graphics windows if I start SSH with -X. So I'm exiting here using this, and if I'm saying -X, then I would also have any graphic windows that would open on this remote machine appearing on my local machine. So basically I could work on this remote machine, which might be a more powerful machine for computing something, for instance, training neural networks. So I can let this machine do it in number crunching and then see the results once it's done on my local machine. So very practical. Yeah, so this remote machine must be running an SSH server for this to work. Sometimes they are running by default, but usually you have to activate it. And it works even, for instance, if you have a Raspberry Pi. The Raspberry Pi runs also Linux, and Raspberry Pi even has an SSH server, but you need to activate it in the settings. And then you can log into your Raspberry Pi just as I showed you. Right, so this is particularly useful because often the Raspberry Pi is built into some hardware, and it doesn't have a keyboard or display connected to it, and in this way you can control it anyway, right? Because it's connected to a wireless LAN, for instance. Yeah, to test if a computer is listening, you can use the command ping. Right, ping just sends a package to a remote computer, and then the remote computer says, "Okay, I'm listening," and then you can see it, and you can use that, for instance, to test the latency in the network. Yeah, so it sends the data packet, and the computer returns another one. So, for instance, I can try this. I can use the machine here. Ping. So here you can now see my computer is alive, and it has a time of 56, around 50 milliseconds here, you can see. So this is similar to the time it took to Hochschule Sachsen-Anhalt. And that's because it seems most of the time is lost getting into the DFN, the Deutsche Forschungsnetz. Okay, Control C stops it. So this way you can test connections. Yeah. And email is another important application in the internet, and actually also one of the earliest ones. SSH was already also quite early, similar to the email. And it uses another protocol. It uses the Simple Mail Transfer Protocol, SMTP. You can also read more here about it. And SMTP again uses the TCP protocol, and usually port 587. And sometimes the old port 465. those ports are a kind of logical channel for the machine to distinguish between different services and applications. Right, so it's very easy. Instead of having a different frequency, here you just have a different port. Yeah, in Python there is also a library for this purpose. So you can actually use email inside your programs using this library smtplib. Right, and it's described here. And also here in this tutorial. So you can use Python to send email, for instance. For instance, if you have a program running on your Raspberry Pi somewhere, measuring, for instance, temperature, and then if a temperature exceeds a certain range, then it sends you a message, for instance. Yeah, so now we come to multimedia on the internet and the World Wide Web. There's actually also a precursor, which is called Gopher, which was invented in 1991 at the University of Minnesota for remote terminals, called VT100. So they had a keyboard and a display, no graphics and no mouse. And the problem is, it's not such a simple user interface. Right? It's good for programmers, but or people writing text, but not for graphics or for making connections, like links. So that's why the World Wide Web was invented by Tim Berners-Lee. He is a physicist at CERN, which is a nuclear research center in Switzerland. So here you can also see the World Wide Web is not the same as the internet. The internet existed long before the World Wide Web was invented. The World Wide Web is just basically the system of presenting graphics and links and to use browsers. So basically the invention of browsers is the World Wide Web. Yeah, the goal here is the networking of information, of documents, of papers. We already had documents. So initially this project had only limited support, and he created a prototype with the help of students, usually summer interns, and they had the first prototype in 1990 on a Next computer with a Unix operating system. Remember, Next computer was the company founded by Steve Jobs after he was fired from his own company, Apple, and before he was rehired. And Next was actually an excellent computer, already based on the Unix operating system. And when Steve Jobs rejoined Apple, then the Apple operating system also became Unix-based, BSD Unix-based. So basically, Apple computers later became descendants of the Next computers. So you could say the Next computers are early versions of Apple computers. And what was important is that they had, because they used Unix operating system, powerful networking capabilities, and at the same time they had very powerful graphics capabilities. So that is something that Steve Jobs added. So he developed HTML, hypertext markup language, HTTP, and libraries for browser development. So basically the main output of this project was again the protocols, the principles. And the actual development of browsers were done by different groups and peoples. And he founded the World Wide Web Consortium, W3C, at the Massachusetts Institute of Technology Laboratory for Computer Science, short MIT LCS, with the participation of the French Institut National de Recherche en Informatique et en Automatique, INRIA. Here you can also see more about the history in German. Yeah, and that led to the development of browsers implementing all those protocols. So by defining HTML and publishing libraries for browser development, a number of browsers were created. First was Mosaic in 1993 at the National Center for Supercomputer Applications, NCSA, at the University of Illinois in the US. Then later was the Netscape Navigator, 1994, by Netscape, which was founded by Mark Andreessen of Mosaic and Jim Clark of Silicon Graphics in Mountain View, California. Netscape also brought extensions to the HTML protocol, and it led to a strong growth of Netscape. And because of the success of Netscape, Microsoft joined the bandwagon in 1995. So before that, Microsoft said, we don't need networking. We are happy with writing letters locally. But then they found, oh yeah, this takes off. Maybe there's business in it for us. So they came out with the Internet Explorer in 1995, basically copying everything that Netscape did. Yeah, and they also gave away the Internet Explorer for free for servers, and that was basically the business that Netscape had before. The browser were for free, but the servers were for purchase, so companies had to pay for it. But Microsoft gave away everything for free, and that basically destroyed the business of Netscape. So that's why they decided in 1998 to release the Netscape code as basically open source, managed by Mozilla, right? And yeah, so they founded the Mozilla Foundation. And then in 2004, the Mozilla Foundation released Firefox, the browser. There's also the Opera browser since approximately 1995, and that is for special applications, for instance, mobile phones. There are also text-based browsers, and that's useful for small computers or for SSH connections, or to extract information from web pages within a program. Right? For instance, if you have a program to check for the weather at a certain location, then you could use this to access a web page which has the weather information, and then it extracts this weather information from it to further processing. Yeah, examples are links or links to. So in the terminal you type, for instance, links and then the address, so we can try it. Oops. So copy, going back to my terminal. So cookie, allow, yes, allowing this cookie, another cookie, allowing cookie. Yeah, so here you can see you have full control over everything. So here you can now use your arrow keys to control everything, and yeah, mouse is not really working. Yeah, so in this way you have a simple text-based browser. So Q for quit. Allowing cookie. You can see there are plenty of cookies. Email address. Yeah, okay. Control C ends it. Right. Oh yeah, we could also try what is my IP. Let's see. Links. What is my IP.com? Cookie. Allowing cookie. Another cookie. plenty of cookies. Yeah, so let's see. This is now the website. Speed test IP lookup. So this is actually what we want to have, right? IP lookup. Yeah, it's not so easy. Ooh, okay. All right, so in principle it would work, but it's not so easy. Basically, here you have to be careful to learn the keyboard control for it, because this is not working with mouse control. Okay, so let's come to the next protocol, the HTTP protocol, Hypertext Transfer Protocol. So this is a request-response protocol between clients and servers. An HTTP client initiates a request by establishing a connection via transfer control protocol to a specific port of the remote host, and port 80 is the default. So the client here is our computer which runs the browser. And if we type in the web address, then basically we try to establish a connection to the server. And we do that using, again, the transfer control protocol, TCP, and using a specific port, port 80. And this tells the server on the other side that we are looking for a web page, right? So that we are using HTTP and we are looking for a web page. And this HTTP protocol specifies the required resources using the so-called Uniform Resource Identifier, or URIs, or URLs for Uniform Resource Locator, using HTTP or HTTPS. Yeah, so if you type HTTP or HTTPS, then basically this tells the server that we are looking for this website. And HTTP has evolved into several mostly backward compatible versions. And HTTP/3 is the current version, and you can read more about it in this Wikipedia link. Yeah, so HTTP is for the communication to the server, and HTML is the hypertext markup language, and this displays the web page in our browser. And this was originally developed based on SGML, and we come to it soon. Hypertext markup language, HTML, is a markup language for the creation of websites. And this is standardized by the World Wide Web Consortium. And newer developments are XHTML, Extensible Hypertext Markup Language. And this is a markup language that has the same expressive possibilities as HTML's, but a stricter syntax. And XML, for Extensible Markup Language, is a World Wide Web Consortium recommended general purpose markup language for creating special purpose markup language, capable of describing many different kinds of data. And this is derived from SGML. And it's a simplified subset of the standard generalized markup language, SGML. Yeah, so you see, it's also not falling out of the blue sky. It's actually a subset of SGML, which was there before. And the primary purpose here is to facilitate the sharing of data across different systems. And here another link from NetPlanet. So this mentioned SGML is a descendant of IBM's generalized markup language, GML, which was developed in the 1960s by Charles Goldfarb, Edward Mosher, and Raymond Loewy, and whose surname initials also happen to be GML. HTML was originally designed to enable the sharing of machine-readable documents in large projects in government, legal, and the aerospace industry, which have to remain readable for several decades, a very long time in information technology. Right. So here it's about documents, text, formatting, pictures. So basically something like PDF would do for us now. And this is based on HTML or GML. So yeah, quite similar to basically also what HTML is doing. HTML gives us formatting information, text size, where to put the text, graphics, pictures, and represents it in our website. So basically these are capabilities that were there before, but they were just adapted for HTML. Yeah, and in turn HTML is based on the ASCII text format, which means when you look in the website at the source code, you can see it's text. You can actually read it. You have keywords, then you have the text which appears in the web page, and you have commands on where to put an image and what size to put it. So you can actually read it using an editor, and you could also change it. For instance, change the size of a displayed image by changing their scaling, or the size by just changing the numbers in the text. Yeah, so it's all based on the ASCII text format. And the ASCII text format in turn consists simply of codes for the keys on a keyboard. Right? Everything you can type on the keyboard is turned into a code, usually on the keyboard itself already. So then what's transmitted through the cable to the computer is already the ASCII code. And this is also a very early standard in computer technology, and it's used for programming languages. So already at the time when people were programming in the early languages like Fortran, it was based on the ASCII text standard. And that's why we have this long-term stability. ASCII is ASCII. It was ASCII 50 years ago and will be still ASCII in 50 years. Yeah, so HTML is also an ISO standard, International Standards Organization. It also has this number here. It's called Information Processing, Text and Office System Standard Generalized Markup Language. And it's primarily intended for text and database publishing. And one of its first major applications was the second edition of the Oxford English Dictionary, which was and is wholly marked up in HTML. Yeah, so something that we would do nowadays, for instance, in LaTeX. Yeah, so and indeed it's related to LaTeX, the word processing system for scientific documents. So LaTeX is perfectly suited for example, writing equations. And this is open source and available for Linux, Unix. There's actually part of the operating system, and also Windows. And a practical tool, for instance, is TechMaker. TechMaker is a program which you can download, and it uses LaTeX inside. So here's an example how a LaTeX text would look like. You have command words like \begin document. Then here's the text that appears in the output. This is text. Here you have a formula. So formula are done in a formula commands. So here starting \square bracket. Then here's text from the formula equals \frac. This is a fraction a over b, and then here's end document. And the output would be formula equals a divided by b. So you can see here you have those commands to tell how to set it. Yeah, HTML is quite similar, but you have different command words. Yeah, so our recommendation is write scientific papers in LaTeX. For instance, the media project, the student research project, the diploma thesis, the master thesis. This way you also get more stability, which means even in years to come, it is still readable and you can still use it. Yeah, and that should be it for today. Thank you for your attention, and then see you next time.